There are moments in the universe so powerful, so vast, that even our most advanced instruments struggle to fully grasp their scale. Among the most cataclysmic are supernovae, stellar explosions that can outshine entire galaxies and unleash energies beyond our wildest comprehension. But now, astronomers are witnessing something that defies precedent. In the year 2025, the largest known supernova explosion in recorded history is unfolding, and it may forever change how we understand stellar death, cosmic evolution, and the very fabric of space-time itself. This event, which has captured the attention of astrophysicists around the globe, is tied to a mysterious star system located billions of light-years from Earth. The supernova, catalogued as SN 2025Z, is not just massive, it's rewriting everything we thought we knew about how stars die. Unlike typical supernovae, which tend to emit their energy in brief, violent bursts lasting days or weeks, SN 2025Z has sustained a colossal release of light and radiation for over 3 years. Even more shocking, its luminosity continues to increase rather than fade, suggesting that something far stranger is occurring at its core. Using the combined power of the James Webb Space Telescope, the Chandra X-ray Observatory, and a host of terrestrial observatories, scientists have been able to observe the supernova in unprecedented detail. What they found astonished them. The explosion's energy output is not just immense, it rivals the energy emitted by entire galaxies. And the shape of the blast appears asymmetric, hinting at powerful magnetic fields or unknown physical processes altering the detonation structure. At the heart of this cosmic upheaval is a hypergiant star, believed to have been over 300 times the mass of our Sun before its collapse. These kinds of stars live fast and die young, burning through their nuclear fuel in mere millions of years, compared to the Sun's projected 10 billion-year lifespan. As the star neared the end of its life, its core began to fuse heavier and heavier elements, until it could no longer support its own mass. Gravity won. The star collapsed inward, and then, violently, rebounded outward in a supernova. But SN 2025Z isn't just a large explosion. It's something even more exotic. It may be the first pair instability supernova ever observed at this scale. In such events, the internal pressure of a massive star becomes so extreme that gamma rays within its core spontaneously convert into pairs of electrons and positrons. This reduces the radiation pressure holding the star up, causing it to collapse and then explode in a way that completely annihilates the star. No neutron star. No black hole. Just scattered atoms. However, there's a problem. SN 2025Z is still visible, still brightening, and seems to be producing radiation signatures inconsistent with the pair instability model. The emissions include not just high-energy X-rays and ultraviolet light, but even structured radio waves, which some suggest might be shaped by the presence of a strong magnetic engine, possibly a magnetar, a rapidly spinning neutron star with a magnetic field a quadrillion times stronger than Earth's. If true, this would imply that something survived the explosion, possibly challenging the pair instability scenario entirely. Astrophysicist Dr. Lena Raskova, who leads a multinational team analyzing the data from James Webb, shared in a recent conference, "This is not just a supernova. It's something we've never quite seen before. It's as if the universe is trying to tell us a secret we weren't meant to know yet." And here's where the mystery deepens even further. The radiation from SN 2025Z isn't uniform. It pulses. It fluctuates in a rhythm. Some researchers argue it resembles quasi-periodic oscillations, waves of energy that could indicate that the core of the explosion is collapsing into a black hole in slow motion, while still interacting with the surrounding stellar debris. Others claim the pulse pattern may be evidence of gravitational lensing, the warping of light by intense gravity, possibly caused by massive unknown objects situated between the explosion and Earth. Even more chillingly, some theorists suggest that we may be witnessing a failed transition between dimensions. According to certain models in theoretical physics, supermassive collapses could potentially punch holes in the fabric of spacetime, allowing for brief glimpses into higher dimensional structures or creating what's known as a naked singularity, a point of infinite density visible from outside a black hole's event horizon. Such a discovery would upend Einstein's theory of general relativity and imply that our universe is not the sealed system we once believed. But as much as this event opens new doors in theoretical physics, it also raises existential questions. What happens when stars this massive die? Could similar stars exist closer to our galaxy, perhaps hidden within the Milky Way's dense core or obscured behind dark dust clouds? If a hypergiant star like the one behind SN 2025Z were to detonate near Earth, even within a few thousand light years, the gamma radiation alone could strip away our ozone layer, triggering mass extinctions. Indeed, some scientists have speculated that Earth has felt such impacts before. Elevated levels of iron-60, a radioactive isotope created only in supernovae, have been found in ocean sediments and Antarctic ice, suggesting that a nearby supernova may have occurred around 2 to 3 million years ago, potentially influencing the course of evolution. Still, SN 2025Z appears to be a one-of-a-kind event. Its location, over 10 billion light-years away, means it occurred when the universe was just a few billion years old. We are seeing light that has taken most of cosmic history to reach us. But despite its distance, the implications are immediate and profound. NASA, ESA, and other agencies have allocated emergency resources to continuously monitor the supernova. Amateur astronomers with powerful enough equipment are also being invited to contribute data, making this a rare citizen science opportunity. Scientists hope that as SN 2025Z continues to evolve, they can gather critical data about the structure of massive stars, the physics of core collapse, and perhaps even the nature of dark energy, which seems to be interacting with the shockwave in subtle but measurable ways. Some researchers are even considering the possibility that this event could shed light on the origin of matter itself. In the milliseconds following a supernova, temperatures and pressures reach extremes not seen since the Big Bang. It is in these infernos that the heaviest elements in the universe are forged: gold, uranium, and even some isotopes of carbon. Without supernovae, planets like Earth, and life as we know it, would never have formed. Yet SN 2025Z appears to be creating more heavy elements than expected, possibly hinting at a different internal structure, or even exotic matter being created during the collapse. This opens up the tantalizing idea that we may be seeing the birth of new physics, as yet unaccounted for by the standard model. What does this mean for the future? For one, it reignites the importance of space observation in an era where AI and machine learning are now being applied to cosmic data in real time. Algorithms trained on petabytes of supernova simulations are being fed the data from SN 2025Z, and what they are beginning to see doesn't always match expectations. Anomalies keep surfacing: variations in neutrino emissions, unexplained absorption lines, and fluctuations in local spacetime measurements that are, for now, completely unexplained. Could this be the first sign of a cosmic-scale quantum event? Could the supernova be a trigger for something even bigger, perhaps the birth of a black hole that grows into a quasar, a beacon that will shine across the cosmos for billions of years? Or might it be the formation of a primordial black hole, something only theorized to exist in the early moments after the Big Bang? Some even whisper more speculative ideas. Could the pulsed emissions from SN 2025Z be artificial? Could they represent a civilization's failed attempt to harness stellar energy on a galactic scale? A Kardashev Type II civilization pushing the limits of astrophysical engineering and paying the ultimate price? While most mainstream scientists remain cautious, the possibilities are staggering. And whatever the cause, SN 2025Z reminds us of one thing: the universe still holds secrets. Secrets so large, so violent, and so mysterious, that even with all our technology and understanding, we remain humbled by the cosmos. As we at Discovery at 2.0 continue to monitor this unfolding event, we invite you to join us on this journey. The largest supernova ever observed is not just a story about distant stars. It's a glimpse into the forces that forged us, the laws that govern existence, and the boundless scale of the universe we call home.